In this lesson, we are going to talk about the basic concept of Taylor series. So before we talk about Taylor series, we have to recall one thing that we learned from the previous lesson. So in the previous lesson, I gave you a function, right? So in the previous lesson, you have a function, and I said that it is possible to write this function as a series. So one function that we studied in the previous lesson is 1 divided by 1 minus x. So that is a rational function, and then you learn this type of function back into pre-calculus or intermediate algebra. But in a calculus, I say that the 1 divided by 1 minus x can be represented by a series. So the expansion of the series, look at the blue handwriting. So the second line, that is 1 plus x squared plus x to the third, x to the fourth, x to the fifth, x to the sixth, so on and so forth. So overall, the series is summation. N goes from 0 to infinity. We have x raised to the nth power, and this series is convergent when the base, the absolute value of x, is less than 1, because this is a geometric series. So we talk about the pink series in the previous lesson, right? So in this lesson, to understand what Taylor series is, I am going to give you an exponential function e to the x. So look at the yellow handwriting. So the e to the x, you learn this type of function back into intermediate algebra and pre-calculus. In calculus, I say that the exponential function e to the x can be represented by a series. The expansion of the series is 1 plus x raised to the first divided by 1 factorial plus plus x squared divided by 2 factorial plus x to the third divided by 3 factorial, and then you keep adding. So overall, the series is summation. N goes from 0 to infinity. In the numerator, we have x raised to the nth power. In the denominator, we have n factorial. So the difference between the yellow and the blue is the yellow has a denominator which is n factorial. So let's take a look at this series. So what happens when n is equals to 1? So for when n is equals to 1, the series goes from 0 to 1. So when n is equals to 0, you have x raised to the 0 power divided by 0 factorial, which is 1 over 1. 0 factorial is equals to 1. So you have a 1. When n is equals to 1, you have x raised to the first divided by 1 factorial. So if you take a look at the expansion of the series again, so what you see is when you select an n, right? So when you select an n, so you are basically taking having a polynomial, right? So what do we have when n is equals to 1? 1 plus x divided by 1. So overall, you have 1 plus x. Do you see the orange function in the box? So when n is equals to 1, you have a linear function, right? What about when n is equals to 2? Don't look at the graph yet. When n is equals to 2, you need to take the x squared divided by 2 factorial. I don't really care about what the x squared is divided by. So when n is equals to 2, you have to take the next term, which is x squared divided by 2 factorial. So that means, listen to me, when n is equals to 2, you have a second degree polynomial. All right? What about when n is equals to 3? You have to take the next term. That means you have to take x raised to the third divided by 3 factorial. So that means when n is equals to 3, you have a third degree polynomial. What about when n is equals to 4? Then you have a fourth degree polynomial. When n is equals to 5, you have a fifth degree polynomial. So that means if I change the n from 1 to 5 in the orange box, you expect to see a fifth degree polynomial. A fifth degree polynomial is up. That means a polynomial, the highest degree, is x raised to the fifth. And then there is a picture. I sketched the graph of the exponential function and the orange function, 1 plus x, that is a linear function, right? So let's take a look at the overall idea of Taylor series. So that is, I wrote everything down because they are so important. I don't want to just say it. I want to say it and write them down. If a point chosen on the coordinate plane, which is the xy plane, then it is possible to guess what a function will look like in the area around that point. This is done by taking the derivative of the function and adding them together. The idea is that it is possible to add infinite number of derivatives and come up with a single finite sum. The infinite number of derivatives is what we are going to practice when we do example. So what does that mean? You have the graph of e to the x and a linear function. So what can you say? Listen, when n is equals to 1, the expansion of the series gives you 1 plus x. That is a linear function. I am not trying to say that the linear function looks like e to the x, but do you still remember this? When n is equals to 2, we have a second degree polynomial. That means we expect to get a parabola, right? When n is equals to 3, then we expect to get a third degree polynomial. When n is equals to 4, then we expect to get a fourth degree polynomial. So eventually, we are going to get something that is not a straight line and then not a parabola. We expect to get something like this. Like, look at this curve. We expect to get something like that, right? A curve. So what that means is when n is large. What is n is large? Look at the orange handwriting. So when n is large, that means we have a higher degree polynomial. The concept of the Taylor series is that the higher degree polynomial, the graph of that high degree polynomial is very similar to the graph of e to the x. I know when n is equals to 1, you have a straight line, you compare a curve to a straight line, you cannot say the straight line is similar to the curve. I understand. What about n equals to 2, n equals to 3, n equals to 4, n equals to 5, or n equals to 10? Do we agree that when you increase the n, that means you are going to get a higher degree polynomial? That means you are going to get a curve. You are no longer getting a straight line. The Taylor series is trying to say that when n is high, the graph of the expansion, the graph of the polynomial, which we call it a Taylor polynomial, again, when n is large, you get a higher degree polynomial. The graph of that polynomial, which we call a Taylor polynomial, is very similar to the graph of the given function. That means using this example, let's say you let n equals to 10, n equals to 20, then you get a 10th or 20th degree polynomial. The graph of that polynomial is very, very similar to the graph of an exponential function. How high should I let n be? Higher is better. That's why the series goes from n to 0 all the way to infinity. When n is equals to 0, you get a 1. It's not similar at all, right? So higher is better. N equals to 1, you get a straight line, still not that similar. N equals to 2, you get a polynomial, still not that similar, but better. When n is equals to 3, equals to 4, equals to 5, equals to 6, 10, 1,000, you are going to get a graph that is very similar to the graph of the exponential function e to the x. So that is the general concept or the big picture of Taylor polynomial. And then here is the definition. So we call this Taylor series because the series is invented by an English mathematician called Brooke Taylor. So a Taylor series can be used to describe any function, f of x, a function you learned in the past, e to the x, ln, whatever that is, sine of x, cosine of x, all right? That is a smooth function. What is a smooth function? Smooth function, this word you expect to hear that very frequently in the future lesson. A smooth function is indefinitely differentiable. That means you can take the derivative infinitely many times. The second derivative, the third, the fourth, the fifth, the sixth, you can keep taking derivative. You don't see sharp point, you don't see a curves, you don't see a vertical asymptote, so the function is always differentiable. The Taylor series is used to describe what the function looks like in the neighborhood of the sum number a. So the function f of x is equals to the summation. So here is the Taylor series. In the numerator, you have fn. What is n? The n is the nth derivative. So f of n of a, and then divided by n factorial. Other than that, you have x minus a to the nth power. So let's take a look at the expansion. So when n is equals to 0, 0 factorial is 1, and then if you have a non-zero raised to the 0 power, so that is 1. So when n is equals to 0, so I should write this out for you. So when n is equals to 0, we only have a f of a. When n is equals to 1, we have that. So the 1, do you see that there is a blue one right here? So this is actually not the first power, that is the first derivative. So divided by 1 factorial, and then x minus a raised to the fourth power. And then when n is equals to 2, so this 2 is actually the second derivative. And then the denominator is 2 factorial x minus a raised to the 2. And then when n is equals to 3, the top the function, you have a triple prime of a, and then divided by 3 factorial x minus a to the third, and then so on and so forth. So the n is the green number. All right. And then we have n equals to 4, and then n equals to 5, so you will get a higher degree polynomial, right? So the right hand side, the expansion of the series, we call that an nth degree Taylor polynomial. Just like back to this problem, I took n is equals to 1, so we have a first degree. We don't call that a polynomial. The first degree, we call that a linear function, right? Second degree, we call a quadratic function, but third degree, fourth degree, or higher, we just call that a polynomial. So this one, if you want to take a look at the graph for the exponential function, you can let n equals to 10, n equals to 20, n equals to 30, but you expect to graph a function, a 30-degree polynomial is pretty long. It has 31 terms, all right? The graph of that Taylor polynomial is very similar to the graph of e to the x. That is the concept of Taylor series. All right, and then I also mentioned that what happened when a is equals to 0. So a is usually a number provided in the problem. When a is equals to 0, this Taylor series is called a Maclaurin series, and then is named after a Scottish mathematician called Maclaurin. All right, so regarding the concept of Maclaurin series, let's put that in a separate video. All right, so and then this is the end of the introduction to Taylor series. If you think my instruction is helpful, let me know in the comment section below. Like the video, subscribe to the channel, share the video for me. Appreciate your help. I will see you all in the next lesson for the Maclaurin series. Signing off for now. See you there.